In this video, I am going to demonstrate how to integrate 2 or more BNO055 sensors with one ESP32 microcontroller using a multiplexer. Once the data is extracted from multiple sensors, ESP32 will package all the data in a single JSON and transmit it to Unreal Engine for visualization. This is a continuation of the previous episode where I have worked on a single BNO055 which is mapped with a cube in Unreal. I will be making changes in both the Arduino code and Unreal blueprint to map multiple sensor data to corresponding Unreal cubes. If you have not watched the previous video, please check the description below. You can also visit to my Patreon site to read the complete paper. Here are the steps I will follow to achieve the outcome. At first, connect my ESP32 to a I2C 8-to-1 multiplexer. Then, I will connect my BNO055 sensors with the multiplexer for ESP32 to access individual sensors and access the data. Once the data is extracted from the sensor, I will make a single JSON object with all the sensor information. And using asynchronous UDP protocol, I will transmit the data to Unreal Engine. Finally, to visualize the data in Unreal, I will map the sensor's details to multiple cubes rotational angle. A lot to cover in one video, so let's get into it. If you are new to this channel, please consider to give a like and subscribe. That means a lot to me. Before I start making changes in the code, I have done housekeeping to make my code clean and simple. I am using the same source code from the previous episode. If you are following me, you can download the same source code from my Patreon site. At first, I need to separate the functions in multiple files in Arduino to avoid overloading and create confusions. The sensor orientation estimation to evaluate the pitch, roll and yaw are defined inside the loop function. There are several global variables are defined to store the transient values like theta measured, theta g, pi g, etc. My target is to implement multiple sensors with one ESP32 controller. It means each sensor will have its own cache to store the value for next reading. That means just segregating the functions will not help. To implement it efficiently and effectively, I need a class which will have an instance specific values to the sensor, and the instance will store all the values for next reading. Before I implement the class, at first I need two files. Here I have created two files called sensor.h and sensor.cpp. To create a new file in Arduino, you can simply click on the down arrow button located at the end of the tabs. In the sensor.h, at first I have defined the name of the header by #define sensor_h. This is a basic structure of creating a library in Arduino C++ programming. Here I am defining the header if not defined. To close the #indef at the end, I have given #endif. Inside the defined block, at first I have included all the relevant headers and created a class called sensor. All the global variables related to the storing the values for the next reading I have copied inside the private variables. These variables will not be exposed externally. Here in the private block, I have created a variable called sensor of the object type Adafruit BNO055. My plan is to store the sensor object inside the class. To store the sensor object in the class, at the constructor I have passed the sensor object and the name of the sensor. Some of the initialization were also defined in the setup function of .ini file, such as sensor begin, get temperature, set crystal use, etc. For that, I have created a public function called initialize in the sensor class, assuming the function will be called post the constructor of the sensor. The variables will be accessed from the sensor externally to construct the JSON like name, pitch, roll and yaw, along with the calibration details. I have defined it as a public variables as of now. Finally, to get the orientation update, I have created a function called getOrientation. This function will be called from the loop of .ini file, which will update all the publicly accessible variables. Now let's move to the class implementation. At first, I have included the header sensor.h. In the sensor constructor implementation, I have updated the name of the sensor and the sensor object. Only name will be accessible from outside. Sensor object will not be accessible from outside as I have defined it as private. However, inside the constructor or from any other function, there is no difference in accessibility of any variables. We can use the variable just calling it by name. In the initialize function implementation, I have copied all the sensor related definition or functions like begin, get temperature, set crystal use from the setup function. Finally, in the get orientation function, I have copied all the code from .inr loop functions implementation, and my class implementation is ready to be used. Let's move on to the .ino file. At first, I have included the sensor.ah at the beginning. Then I have created the sensor object from the sensor class and passed the Adafruit BNO055 object to the constructor. In the setup function, after the Wi-Fi connectivity, I have called the sensor initialize function of the class object. This will call my implementation class and initialize the sensor. Finally, from the loop, I have called the get orientation function first and then printed all the publicly available values in the serial monitor. That's it. The .ino file looks like neat and clear, and it is ready. There are various ways to segregate the functions without creating a class. This path I have taken is more object oriented and clean implementation. In the serial monitor, I can see the JSON is nicely printed, same like before. That means the functionality is not broken and working as expected. To validate the same, let's visualize the output in Unreal Engine. Here in Unreal, I can see my sensor orientation, which is as same like the way I am rotating the sensor. It is responding accurately with pitch, roll and yaw. So far all worked. Now we have proper class and object structure. It's time to implement multiple BNO055 sensor with one ESP32. My BNO055 is connected with ESP32 with I2C mode. As I found the perfect I2C sensor and I want to wire up 2 or 3 or more of them to one ESP32. But this cheap BNO055 has a fixed I2C address 28. And from what I know about I2C, I cannot have two devices with the same address on the same SDA and SCL pins unless I change the device address. This is little complicated, and to avoid that, I have chosen a path of I2C multiplexing. On the same I2C port, Adafruit TCA9548A 128 I2C multiplexer solves the address conflict and enables the normal communication with multiple same address I2C devices. There is no hard and fast rule to use Adafruit products. I can use other products for that as well, like DFRobot Gravity I2C multiplexer. Although it is cheaper and works fine with BNO055 and ESP32, but I prefer to stick to one vendor for all the devices. Now let's move to see the functionalities of TCA9548A. A way to get up to 8 same address I2C devices hooked up on one microcontroller. This multiplexer acts as a gatekeeper, shuttling the commands to the selected set of I2C pins without command. Using it fairly straightforward. The multiplexer itself is on I2C address 70, but can be adjusted from 70 to 77. And I simply write a single byte with the desired multiplexed output number to the port. Any future I2C packets will get sent to that port. In theory, I could have 8 of those multiplexer on each of 70 to 77 addresses in order to control 64 of the same I2C address parts. The chip itself is 1.8 volt to 5 volt compliant, so that I can use it with any logic level. VIN is the power pin. The sensor chip uses 3 to 5 VDCs. To power the board, we can give the same power as the logic level of my microcontroller. GND or ground, common ground for the power and logic. I2C control side pins are SCL. This is the I2C clock pin for the chip itself, connected to my microcontroller I2C clock line. SDA is the I2C data pin for the chip itself, connected to the microcontroller I2C data line. A0, A1, A2, these are the address selection pins for the multiplexer. There are 8 set of SDA and SC pins from SD0, SC0 to SD7, SC7. These are multiplexed pins. Each one has a completely separated I2C bus set. So I can have 8 I2C devices with identical addresses as long as they are on one I2C bus each. To solder the TCA9548A, I have placed the breakout board over the pins so that the short pins poke through the breakout pads. The name TCA95A facing towards up and then soldered all the pins. Soldering nowadays become very easy for me, which you can see it from here. Now it's time to wiring it up. To create the circuit, I have made some modification in the breadboard. Here I have connected ESP32's 3.3 volt to the positive side of the breadboard, and the same is also wired to the other side of the board. Similarly, ground is connected to the negative side of the board and wired up to the other end of the board as well. From the other end, I have connected positive to VIN and negative to the ground of TCA. To complete the circuit, I have connected ESP32's SDA to TCA's SDA and ESP32's SCL to TCA's SCL. I am keeping the same color code standard which I am following since beginning. This completes the connectivity of TCA with ESP32. Now it is time to connect one BNO055 with the TCA. To establish the connectivity with BNO055, on the same breadboard, I have connected the positive and the negative line of the breadboard to BNO055's VIN and ground. TCA Multiplexer supports 8 different slaves of same address I2C devices. To start with, I test one BNO055 first and then connect other one. I have connected SDS7 of TCA to SDA of BNO055 and SC7 to SCL of BNO055. This completes the wiring. Now it's time to test the wiring. The TCA9548A multiplexer has an I2C address 70 by default, and we can send a command to tell which I2C multiplexed output we want to talk to. The coding is simple. No additional library is required to be installed for that. Here in the code, I have defined a variable TCADDR of 70. At first, I have defined a little helper function for TCA to select the port and check the sensor in that port. This function will accept the port number and initialize the sensor by the TCA every time before it reads the sensor data. In the setup function, I have initialized the wire, and in the for loop, I am checking if any sensor associated to that port or not. If the sensor is connected to that port, then I am printing the sensor address in the serial monitor. Finally, in the loop function, I have commented all the code for the time being. On running the sketch, I can see my BNO055 is correctly identified in the port 7 with an address 28, which is as per the expectation. Now it is time to read the sensor data and validate with the previous result. To do that, at first, let me read what BNO055 gives as a sensor details after setting up the port. Here I have declared a private function in the sensor.h file called display sensor details. This function will be called after initializing the sensor. As this is an internal function, I made it private. In the sensor.cpp file, I have implemented the function. Here in the implementation, I am just printing all the details coming out of the sensor, including name, driver version, sensor ID, and so on. Finally, I have called this function from sensor initialize at the end. To initialize the sensor from the .ino file, at first I need the sensor object, which I have declared at the beginning. Please note, default object creation at the global level needs an empty constructor, and hence I have to declare a default public constructor for the sensor class both in the header and the class implementation. Now the default constructor is created, let's call the sensor object as s_upperarm_L. Don't worry about the name as of now, I will make it more significant name later on. Once the sensor is identified by the TCA, then recreate the sensor object with BNO055 and the name. After that, I am calling the initialize function of the sensor. The output in the serial monitor ESP32 has nicely extracted the BNO055 details and printed it. Now it is time to extract the data from the sensor. To do that, I have uncommented everything in the loop function and of course changed the name of the sensor object to upperarm_L. I also have uncommented the connect to Wi-Fi function call in the setup function to avoid execution problem. From the output in the serial monitor, I can see the JSON has printed successfully, and in the Unreal Engine, the cube is moving in line with the sensor. This means we have successfully implemented the sensor multiplexer. Now it is time to add another sensor to TCA. Adding more sensor with TCA is simple. I only need to connect 4 wires: VIN, ground, SDA and SCL. Here you can see how easily I have connected 4 wires with another BNO055. This time I have used SDA6 and SC6 port of TCA. Now let's move on to the code. Same like before, I have created a sensor object at the beginning. This time I have named it s_lower_arm_L. In the setup function, I have added a switch case statement to associate the sensor object to the corresponding code. Finally, in the loop, I have printed both the sensor's JSON data in the serial monitor. Before calling the sensor function, it is required to let TCA know about the port so that TCA makes that particular port sensor activated for ESP. That's it. Now let's test it. In the serial monitor at the beginning, I see both the sensor objects have been identified by ESP32 and nicely printed the orientation detail of both the sensors. Changing the pitch, roll and yaw values are getting updated on changing the sensor orientation. Now it is time to visualize both the sensor data in Unreal. Before sending the data of multiple sensor objects, I had to restructure the JSON data structure. I have already explained about JSON or JavaScript object notation in the previous video. Please check the link in the description below. This time, the data in JSON will contain multiple BNO055's orientation data along with the sensor name, so that in Unreal Engine on receive will know which sensor is sending the orientation, and accordingly it will map to the corresponding sensor model. The final architecture will be little complicated. It means there will be multiple ESP32 will be sending multiple BNO055's data, and the number of BNO055 of each ESP32 may not be equal. Keeping that in mind, it is always better to send sensors data as an object packed inside an array. So the structure I have decided is the main object will have a name, say hand. The side will indicate that which side of that object refers to. Sensors will be an array where all the hand related sensors are packed together. Each sensor object will have name, calibration detail and orientation details. Similarly, if the structure is for leg, there could be left side of the leg or right side of the leg, and there could be 3 or more sensors associated with it. We'll talk about more of this orientation in upcoming videos. This way the data will be clean and easier to read. To do that, I have further modified my sensor class. In the header file, at first I have included Arduino JSON.h. Then I have moved all the public attributes to private, as those will no longer be accessible by the controller. The getOrientation function will now return the JSON document object, which is a particular sensor details. That's why I have added a return type of the getOrientation is dynamic JSON document. I also have added a private function to prepare the JSON output. I made it private because this function will be called internally. Finally, in the .cpp file or in the implementation file, I have implemented the prepared JSON function, which will prepare the JSON object as like the way I wanted. And this function will be called from getOrientation function after the pitch, roll and yaw estimation. Simple coding. Now it is time to serialize the JSON object in an array in the controller file. In the loop function, at first I have created a dynamic JSON document and specified the name as hand and side as left. Then in the sensor node of the document, I have added getOrientation details at 0 and 1 index position. Arduino JSON understands that this way providing the data will be serialized into an array object. Finally, for testing, I have printed the details to the serial monitor after serializing the object. That's it, all of the coding. Very neat and clean. In the serial monitor, I can see how nicely the objects are getting printed. Here is the clean output after indentation. Now let's move on to Unreal Engine for visualization of the data. In the Unreal Engine, as the JSON object structure has been changed, so my blueprint code will also need to be changed. Here in the Unreal, my Unreal Playground project, I have created a new level called sensor test_multi. There is no reason to create a new scene, but I have created this to keep the source code separated for future reference. In the blueprint folder, I also have created another blueprint called UDP controller_multi. I will be using the same cube blueprint class with a different material color. To change the color, I have created a folder called materials, and inside the folder I have created a material class called blue and given the base color blue. More on the material will be in the upcoming videos. Once I placed the cube blueprint on the scene, I made couple of changes. At first, I have given a tag for both the cube class that is same as the sensor name, upper arm_L and lower arm_L. The reason of giving same name is to find the actor by tag before applying the orientation on the object. Now in the UDP controller blueprint, I have extracted the sensor array and then running a loop for each element in the array. Each element of the sensor array returns me the name of the sensor and the orientation. Based on the name, I am searching the actor of the class cube and tag the same name. The getAllActor of class with tag returns an array. For my case, it will be a single element array. So the first element is the one on which I have applied the new rotation. For that, I have used the function setActorRotation. Here on play of the project, I can see both my sensors are actively working as per the rotation of the sensor. On pitch, roll and yaw of each sensor in Unreal is correctly representing the model. This is really amazing. It means multiple sensor multiplexing is working perfectly. This will be a huge cost saving for me. And here you can see two BNO055 is connected to one ESP and sending a data pack with both the sensors together. For the final presentation, like when I will be mapping the sensors with human rigid body, I will be needing 17 BNO055 sensors. And if I could use 3 or 4 ESP32, then all the 17s can be clubbed inside 3 or 4 ESP32 devices. I will be definitely looked into the final prototype very soon. Before that, it is important to project all these BNO055 orientation details to human rigid body. In the next video, I will demonstrate how the sensor data can be retargeted to human rigid body. It is complicated and I am sure it will be fun. I am getting a lot of responses from you and it is really encouraging for me. A big thank you to all of you. If I successfully achieve the outcome, I will definitely give away a suit to all of my followers. Of course, with just production cost, not to profit. I might be wrong and not able to explain it properly. If you could point out those problems or better way of doing it, it will be a great help. So please comment and help me out. On that note, I'm finishing this video here. I hope you like the progress and the strategy of the development. Please stay tuned for such interesting topic and the solution. Till then, stay safe and take care. Thank you for watching.